Welcome to the JRECLips conspiracy. We're going to gently explore the vast and intriguing world of ufology, conspiracies, and all sorts of similar topics. Our approach is a bit softer, a bit more relaxing. So please, just make yourself comfortable. Feel free to take a few deep breaths, and if you'd like, you can even close your eyes. Before you fully settle in, if you happen to enjoy what you hear, consider giving the video a thumbs up or perhaps subscribing to the channel. Of course, it's not necessary at all. And if you feel like it, you're also welcome to let us know where you're watching from and what time it is for you. We are glad you are here. And with that, let's begin.
I've been doing some work on black holes recently, which I hadn't started last time I saw you, actually. So I got interested in it. And the amount of the progress that's been made in trying to understand how they work. And a question that was posed by Stephen Hawking a long time ago, really 1970s, early 1980s, which is what happens to stuff that falls in? But the simplest question you could possibly ask.
Right.
There's progress being made on that now, which I think is profound and exciting.
How is the progress being made? Like, how do we study a black hole?
I mean, it's mainly theoretical, although we have now got photographs of them. So we have two photographs, which are radio telescope photographs.
Right.
One of the one in the center of our galaxy, which is a little one. It's called Sagittarius A star. It's a little supermassive black hole. So it's about 6 million times the mass of the sun, which makes it a little supermassive. And then there's another one, the first photo that was taken, it's a collaboration called Event Horizon. And they took a photo of one in the galaxy M87, 55 million light years away. That thing is around 6 billion times the mass of the sun. I mean, imagine that, 6,000 million times more massive than our sun.
Is that the largest black hole we've ever discovered?
No, there are bigger ones than that, but that's that's the scale of them. It's a big-ish one, that. But if you think about it, I mean, so there's a number, it's called the Schwarzschild radius of the thing. So if you took our sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk within a radius of 3 kilometers, about 2 miles. So you've got to take this thing, which is what I have to convert from kilometers to miles, don't I? But it's about
that's okay. Just say kilometers.
700,000 kilometers. So it's about 500,000 miles radius or something like that. The sun. So you squash it down till it's about 2 miles, and then that would form a black hole.
Wow.
The 6 billion times the mass of the sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is, I don't know, larger than our solar system. Basically,
oh
this
my
thing
God,
that sits in a galaxy. So we've got these two photographs.
Larger than our solar system.
Yeah, the event. Right, so it's a big structure.
Oh,
that's a Chandra X-ray image of. There it is. That's it. So the that one there. That's the M87 black hole. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way. So you think Saturn's rings. So this material is very flat. But what you're seeing in that photograph is the light rays being bent around the black hole from that flat disk. So that was a prediction from Einstein's theory, basically. He published it in 1915. And you can predict that that's what one should look like. And then just about, what was that, 4 years ago now, maybe 5 years ago, for the first time in history, we get an image of one, and it looks like the prediction. So
wow.
It's a remarkable thing.
How phenomenal is that?
Yeah. So we've had those two photographs. The other thing we've had is so-called gravitational wave detections. So these are colliding black holes, and they collide and merge together. And obviously that's quite a violent event in the universe. And so that event, that process ripples space-time. So it sends ripples out in the fabric of the universe, space and time. And actually Kip Thorne, I've spoken to him several times, he's one of the greats, right, won the Nobel Prize for this. And he calls it a storm in time. So you get a time storm. So really, we're to think, as we speak now, there will be these very tiny ripples from violent cosmic events passing through this room, and they're changing the rate that time passes, so that as they go through. And we can detect that now. So we have detectors that can pick that up. And so we've seen those collisions as well.
So these collisions, how far away?
Oh, millions of light years away.
And they're affecting what's happening in this room right now?
Yeah, to a tiny extent. So there's an experiment called LIGO, which is the what it stands for, something like gravitational interferometer. I can't remember exactly what but so basically it's laser beams, and there's one in Washington State, north of Seattle, and one in Louisiana, and they're kind of laser beams, 4-kilometer long laser beams at right angles, and they can detect these very tiny shifts in the. Effectively, you could say the length of the laser beam. It's a bit more fiddly and complicated, but it essentially measures the distortion in space-time caused by these ripples. And it's way less than the diameter of an atomic nucleus, by the way. Way less. These little sort of...
Oh, my God.
And so we've observed many of those collisions. There it is. There's LIGO. Wow. So it's just basically 2 laser beams, but with these ultra-high precision thing. And so we've got data now of the collision of black holes and those event horizon pictures with radio telescopes. So that's part of it. But the main bit has been theoretical advances in understanding exactly... in a sense, it was what's wrong with Stephen Hawking's calculation, which is a weird thing to say sometimes because people think Stephen Hawking surely didn't get his math wrong. But he did, actually, in his calculation. So what he calculated... back in 1973, 1974, is that a black hole, so we picture this thing from which nothing can escape, even light. So when you go in, you're gone, basically. What he calculated is that even though these things are just a distortion in space and time, that's the description of them. So it's almost as if there's nothing there apart from a distortion in space and time. He calculated that they glow, so they have a temperature. So they emit radiation. It's called Hawking radiation. And so important was that discovery. If you go to Westminster Abbey in London, look on the floor of the Abbey on his memorial stone, and he's in there next to Newton and Shakespeare and all these people, and he's there. And chiseled in stone on the floor of Westminster Abbey is his equation for the temperature of a black hole. So it was this tremendously important discovery. So he discovers these things glow, and he calculates how they glow. A very low temperature, but they emit things, which means that they shrink because they're emitting stuff, and so they're shrinking. So that means they have a lifetime. So first of all, one day they'll be gone. So that means that you have to address this question of what happened to all the stuff that fell in. And his calculation said that there's no record at all of anything that fell in all this radiation that's come off the black hole. So it's purely information-less radiation. So what that means is that black holes destroy information, according to that calculation. And that's a big deal because nowhere else in all of physics does anything erase information from the universe. So it's really true that if I got this notepad and pen, right, and I wrote some things on it, and then I set fire to this, even just incinerated it, put it in a nuclear explosion, whatever. In principle, according to all the laws of nature that we know, if you collected everything that came off, all the radiation, all the bits of ashes and things, and you could just measure it all, then just in principle, the idea is you could reconstruct the information. So it all gets scrambled up and thrown out and so in practice you can't do it. But in principle, the laws of nature say that information is not destroyed, it's just scrambled up in a way that you can't reconstruct, right? But this calculation that Stephen did said there is no information in that radiation at all. Zero, just nothing. So it seemed that uniquely in the universe, black holes erase information.
When you say there's no information, like how are you measuring whether or not there's information in it?
So really in bits. I mean, the idea is, and I should say it's very much in principle this, so no one thinks in practice you could reconstruct what I wrote down on this if you set fire to it. But in principle...
Well, maybe sometime in the future, maybe a million years from now.
In principle, you could just collect everything. Then somewhere in that all that radiation and ashes and light that's come off the thing is the information. It's there. So you could reconstruct the book or what I wrote on this page in principle. But the thing about Stephen's calculation was that even in principle, it said there is no information. And by the way, it's kind of easy to see why, actually, because this radiation, this Hawking radiation that comes off the black hole, it's coming from the horizon of the black hole. So I should say what the horizon is, maybe. So it's if you remember, I said that the sun, if you squashed it down within 3 kilometers of radius, you'd get this kind of distortion in space and time, from which, if you went in across this region 3 kilometers, you went inside it, you couldn't get out. So that's called the event horizon. So you wouldn't notice if you fell through the horizon of the black hole in the Milky Way galaxy. If you went into that one, we could be falling through that horizon now in this room, and we wouldn't notice anything, except that we couldn't get out again. And ultimately, in a few hours, in that case, time would end for us. So we just you go to the end of time. We could talk about that. There's a picture of that. Maybe I should talk about this. Is getting quite complicated already, isn't it? We didn't start in a relaxing way, did we? I don't know.
No need to. No need to. Let's get right into it. So we wouldn't notice.
Not for the big black holes. So these supermassive black holes, we could fall across this horizon. It's just like being in empty space for us. So we would just be talking now, when we could have been talking on the outside of the horizon, and by the time I finished the sentence, we could be on the inside of the horizon, inside the black hole. And according to Einstein's theory, at least, which is the theory that predicted them initially, we could just do that. We could just go in, and we wouldn't notice for a bit. The thing we would notice ultimately is you go inexorably, nothing you can do, you go to this thing called the singularity once you've crossed the horizon, and you are going to that thing. And then the question arises, what is that thing? And one answer is we don't know, but in Einstein's theory, it's the end of time. So one way of picturing what's happened here is so distorted is space and time by the collapse of a star or the collapse of loads of stuff to make these big supermassive black holes. We don't quite know how they form, actually, but it's collapsing stuff. So it distorts space and time so much that in a real sense, they kind of flip over. They get mixed up. And so this singularity, which you might have thought of as the point to which this thing collapsed, this infinitely dense point, you might think. But actually, it's more correctly to be seen as the end of time, because everything's got mixed up. So you go to the end of time. And it's just like saying, why can't I escape that thing? It's like, why can't we escape tomorrow? Right, so we are going to tomorrow.
Right.
And if I said to you, let's run away from tomorrow, you'd go, I can't run away from tomorrow.
So is it the end of time because all information is being erased, so there's nothing?
Yeah, I mean, is
that the idea?
If you draw the thing, you can draw a map of it, and it just literally time ends, just purely in Einstein's theory. This is 1915. His theory of general relativity. You just get a line there, a line that says there's no future beyond this line. It just stops.
Okay.
So, I mean, admittedly, that's not. We think there's a lot more to it than that. But
is it just we haven't figured the rest of it out yet?
Well, that's the thing. So we're starting to get hints about what might happen, which is leading us. So to backtrack a bit. Why does this calculation Stephen did? Why has it got no information? Why does it say there's no information in this radiation? The thing is, it's coming from the horizon. So it's there's loads of ways to think about it, but one way is that this weird place, this point of no return in space, that you can fall through, but it's a point of no return. It sort of shakes, it almost disrupts the vacuum of space, and sort of almost shakes particles out of the vacuum. That's one way of thinking about it. But this radiation is coming from the vacuum. It's coming from empty space. Whereas if you think about the thing that I throw in, if I throw this notepad into the thing, then that goes to the singularity. It's got nothing to do, the radiation's got nothing to do with this thing. This thing is not set on fire or something like that. It's gone to the end of time, and just whatever's happened to it has happened to it. So this radiation's got nothing to do with anything that falls in, at first sight at least. And so that was the paradox. It's called the black hole information paradox. It's like, it's one way to put it is the laws of nature that we use to calculate what happens tell us that information is never destroyed. And when you calculate what happens, it tells us that information is destroyed. So that's why everyone got interested in it in the 80s, because it's interesting.
If you enjoyed today's video, let us know in the comments. And if you want more of these, please subscribe. Until next time, you are watching JREClip's Conspiracy.